Okay, so in this question, we are told that we have a steel ball that is dropped onto a very hard floor. Over and over again, the ball rebounds to its original height, and we assume that no energy is lost, of course. That's why it's rebounding to the original height. The question is whether the motion of this ball is simple harmonic motion or not. So let's recall here the the variation of different variables in simple harmonic motion. We know that x will be varying with time, which is the elongation or the height in this situation. And we know that there should be a maximum and then an equilibrium position. And we know that the speed should be changing with time as well, and the acceleration. If we check the situation that we have here, we have this ball and it's falling to the ground and then rebounding back up. If we want to start with the acceleration, we can determine this from the force, right? The acceleration will always follow the variation that is taken by the force. So here the force that's acting on the ball is just the weight and there's nothing else. So if we only have the weight, then this means that it's a constant force. Only weight acts here. So this means that we have a constant force. And then we can deduce that we have a constant acceleration, which is obviously not the situation in a simple harmonic motion. So it's as simple as that. Whenever you see that we have a constant acceleration or velocity, then this means that this is not a simple harmonic motion. We have also here this small question. We have identical springs attached to a box in two different ways. First, the springs are unstrained, they're in equilibrium. Then the box is pulled to the right and released in the two situations. And they told us that the initial displacement was the same. And then after releasing the box, we want to know which one of them will have a greater net force, if either has any larger force. So let's check the forces that are acting on these boxes. We have displaced the box to the right. So we can expect that our spring will be compressed on the right side in this situation and elongated on the left side. While here, both both springs will be elongated. So if we want to draw the corresponding forces, the compressed spring is going to make a pushing force away, and the stretched spring will also make this pulling force towards it, so that the two forces have the same direction, as you can see. In this situation, however, both springs are stretched, so again they will both pull the box towards them to restore their original position and become unstrained again. But as we can see here, both forces, first of all, they will have the same magnitudes because it's the same displacement. And we can see they have the same direction. So if we are thinking of the net force, then the net force is going to be the same in both situations. So we can write over here that the net force is the same. Let's check this question here now. We have a 0.42 kilogram block, and it's attached to the end of a horizontal ideal spring. It rests on a frictionless surface. We are told that the spring stretches for 2.1 centimeters relative to the original length or the natural length. And then when it's released, we have that it possesses an acceleration of 9 meters per second squared, and we want the spring constant. So let's start by just writing the given. We are given that x is 2.1 centimeters, which is 0.021 meters. The acceleration is 9 meters per second squared, and the mass is 0.42 kilograms, and the question is to find k. Like we said, k is equal to f over x, right? We have x, but we do not have the force. But however, we do know that the force is equal to the mass times the acceleration. So we can just multiply the mass by the given acceleration and then divide by this displacement in order to find the spring constant. So the acceleration can help us in finding the value of the spring constant in this situation. And the final answer is going to be 180 newtons per meters. I have one more question here. Two people are pulling on a horizontal spring that is attached to an immovable wall. I'm going to draw the situations here because this is going to be useful in visualizing what's going on. So we have two people pulling, so I can actually draw the forces. This is our first force and our second force, F1 and F2, since we have two people pulling this spring. And then they detach this spring from the wall and pull on opposite ends of the spring. So now we have detached this spring from the wall, and each person is pulling from one end. And the question is, where would the spring stretch more? So the thing here is that if you look at the forces, when the two people are pulling in the same direction, okay, the spring is going to stretch. However, the wall here is going to pull the spring back to oppose the forces exerted by these two people, by Newton's third law. So there will be a force exerted by the wall on the spring, and it's going to be equal to the sum of these two forces. And then the net elongation, if we want to think about this, the net elongation will depend on the net force over k. And this will be the sum of these two forces. But if we look at the second situation, here the first person is exerting a force and the second person is doing the opposing force. So by Newton's third law, we have just F1 and F2 and that's it. And then if we look for the elongation, it will be just one of these two forces, and one of these two forces only will contribute to this elongation, and so obviously we're going to have less stretching here. Okay, so the first situation will have more stretching.